Hello everyone. So today we're going to continue on 8.1 line integrals. So if I remember correctly, our last video we get to see how to calculate line integral using the parameterization. So remember we talked about in class, one of the biggest most unique thing about line integral is that we are trying to actually integrate over multiple dimensions. Like in this example on the screen right now, we actually have a curve that go in R3, and therefore we have dx, dy, and dz to work with. But yet, because we have a line integral, which is by definition a single integral, we actually cannot actually properly integrate all dx, dy, and dz together. Remember, that's why we have iterated integral, where we're going to actually have to integrate 3 times to deal with dx, dy, and dz. So one of the unique thing about line integral is that we will use the parameterization, which is on the side right here, to help us convert x, y, and z all into the parameter t, as well as the differential dx, dy, dz into dt, and therefore allow us to actually evaluate the line integral using a single integration. But here comes an interesting problem. The problem is that, as you probably remember me saying this back in chapter 1, a parametric representation is actually not unique. So what happens if we use a different parameterization? Would that change what our line integral is? And if you think about logically, you should realize that that should not happen, because what a line integral actually represents, a line integral actually represents amount of work being done. And if the way we describe the path is different, will result in the different amount of work being done, then the whole physics system would fall apart. Because that would mean that if you walk the same distance, but you just choose to do it using a different parameterization, now the amount of work is now going to be different between different calculation. And that's really going to break down everything else that you learn in physics. So how do we explain this phenomenon? Well, let's go ahead and try to understand this concept here. So imagine the following. Let's say we're given a path. And let's say the path is defined by this equation. Let's say a very simple equation, y equals x squared, for x go from 0 to 2. So what is this path right here? Well, actually it's pretty simple. It's just basically this parabola that go from here to here. It's 0, 0. It travels along the curve y equals x squared, and you get to the point 2, 4. Consider the following parameterization. And just like with lines that you learned in chapter 1, a curve like this would have different parameterization that we can use. So I'm going to show you some of them, just so that you can see. So consider the following parameterization of this path. Let's say number 1, that's probably the most basic one that I can think of. Let's call it g of t, which will be t squared, and t go from 0 to 2. So essentially what I just did is I take x to make it t, and then y would just become t squared. So that's probably the most simplest parameterization that we can come up with. But that is not the only one though. So show you a second one. So this second one we'll call h, I guess, h of t. And h of t is going to be t squared t to the 4th. So this one also starts from t0, but to get to the point 2, 4, I'm actually going to have to go t from 0 to radical 2 instead. And for no particular reason, let's do a third one. So I'm going to go and call this A, B, C, D, F, G, H, I. No, I don't like I, J, no. K, let's do K. K of t. And how about k of t to be this? Radical tt, which also follow the same exact path. The reason why, because the y coordinate is the square of the x coordinate. And this one, I'm going to actually have to get to 4 in order for me to get to the point 2, 4. These 3 parameterization all give the same exact path. but yet they are all different. So what's different about them? Well, the interesting thing is actually pretty obvious when you look at it. Notice that if you think about t as being a time variable, notice that parameterization number 1 requires only 2, let's say, seconds to go from 0, 0 to 2, 4. But parameterization number 2 will only require radical 2 milliseconds, which is around 1.414, to go from 0, 0 to 2, 4 along the path y equals x squared. While parameterization 3 requires 4 seconds to go from 0, 0 to 2, 4, follow the line y equals x squared. So what's different about these 3 parameterizations is their speed. They all have different speed, which is what's different about them. They all have the same path, but yet they have different speed. This type of parameterization has a name. These 3 parameterizations are referred to as an equivalent parameterization because they give the same exact path, but just take different amount of time to travel the same path. So they're called equivalent parameterization. These 3 parameterizations are called equivalent. So they're not equal, okay, because they're not exactly the same. They're different. They're definitely different parameterization, but they're equivalent in the sense that they give out the same exact path. They're called equivalent parameterization because their image are exactly the same. Now, given that equivalent parameterization provide the same exact image, travel the same exact distance, notice that both parameterization 1, 2, and 3, G, H, and K, they all describe the same path that go from 0, 0 to 2, 4 along the curve y equals x squared. So therefore, they all travel the same exact distance. But only different is how long does it take to travel that distance, which means they have a different speed. And now take a minute to think about work being done, or what we learned about line integral. We learned that when we divide the line integral formulas, we recall that the speed actually get cancelled out because of reusing the speed, which is technically speaking the same as when we normalize g prime. So that speed get taken out of the equation. So therefore imply that in this case, when I have equivalent parameterization, since they provide the same curve, but just different and travel the same distance, but with different speed, and since work is irrelevant to speed, what we know is that equivalent parameterization must give the same line integral value, which is summarized in theorem 8.1.2, which states the following: equivalent parameterization of a curve alpha will give the same values for the line integral over alpha vector f dot v vector x. And if you think about line integral represent work, and since work is independent of speed, and the equivalent parameterization just have different speed, it makes sense that they should give out the same exact value. So now in this case, I could actually also show you what happened to, let's say, a very simple integral of of these three parameterization and show you that they go to the same thing, and show you how actually you can do this line integral without actually using a parameterization. So imagine the following. Let's say we're going to just do something very basic, and we'll just say let the function vector f of xy just to be equal to xy. And I'm going to let alpha be the path from, let's say, 0, 0 to 2, 4, follow along. Y equal to x squared. So that will basically be this picture right here. So now what I'm going to try to do is I'm going to go and try to do each of these parameterization and show you how it works with the parameterization. So here's my first one. So line integral, oh, I forgot. Let's say I'm going to ask you to find the line integral. Okay, so let's go ahead and do this. So line integral over alpha, vector f dot d vector x. So that would basically just be integral from 0 to 2, f of g of t, so become f of t, t squared, dot product, g prime, which is 1, 2t, dt. So I simply just use this formula right here. Oh, right here. This formula right here. Okay. Now, since we choose our vector f to just be xy, so therefore I just basically take whatever we plug in and just keep the same. So therefore it becomes easy. Oop, I forgot a dot product. So basically it becomes the integral from 0 to 2, t plus 2t to the third dt. And so therefore become just 1/2 t squared plus 1/2 t to the fourth. You vary from 0 to 2. And when I plug in 0, it go away. When I plug in 2, it becomes 2 plus 16 over 2 is 8. So I think the answer is 10. Pretty simple. Now let's see if I can get the same result with the other two. So I'm going to do one more. I'm going to ask you to do the last one on your own. Okay, so I'm going to do just the next one, h of t, and show you how that worked, which is equal to t squared t to the fourth, but this one t go from 0 to radical 2 only. So let's go and do my integral. So this will go from 0 to radical 2, f of t squared t to the fourth, vector f, I forgot the arrows, dot product, the derivative of this thing, which is 2t 4t to the third dt. So once again, because the function f just simply just keep x and y, so therefore this just from 0 to radical 2, t squared t to the fourth, dot product 2t 4t to the third dt. So that go from 0 to radical 2, 2t to the third plus 4t to the seventh dt. And if I integrate this thing, it become 1/2 t to the fourth plus 1/2 t to the eighth. You vary from 0 to radical 2. And so that come out to be 2 plus 8, which is 10. So I'm going to ask you to go and try to do the third one on your own, so that way you can see how that works. But what I want to show you is actually something different. So notice that both of these scenarios, what I try to do is simply use the parameterization to help me change d vector x, which is dx dy, into t dt. And that works. But I could actually do the following. So show you this. Now notice that we do know the following. We do know that the curve we try to follow is this one. Not with a parameterization, but just simply know the curve between the coordinate x and y, and also knowing the domain for x. So now let's say we want to evaluate this thing. So how about we do the following? So this basically meaning I'm doing the integral over alpha of the function vector f, which is just xy, dot product dx d vector x, which is just dx dy. So therefore that's just equal to this. And remember, because this is a single integral, I'm not allowed to actually split it into two. Okay, even though there's a plus sign, but because of the two things have different differential, I really cannot split it. So how am I going to evaluate it? Well, how about I do the following? Notice that I do know y is equal to x squared. And if y is equal to x squared, then wouldn't that tell me that dy would equal to 2x dx? And now it seems to me that I have everything I need to change the y and dy into x and dx. And if I do that, I will be able to figure out my integral, because now I won't have one differential with one variable. Okay? Remember, right now the problem is that I have an x and a dx and y and dy. I can't really do anything with that because I only have to integrate once, but I can't integrate both dx and dy at the same time. But now by doing that, I will be able to fix it. So now I can say it's integral from 0 to 2, because x only go from 0 to 2, and I have x dx plus x squared times 2x dx. So that just becomes integral from 0 to 2, x plus 2x to the third dx. And if you have a little deja vu, you should, because that is technically the same exact integral as this one right here. Because remember, in this parameterization g of t, x is t and y is t squared, which is exactly what we just did here. So now the math would exactly work out the same. Okay, so notice that if you do have a formula that can relate x and y together, you can actually directly just use that to solve your line integral without going into parameterization, which is a valid way to solve a line integral, and which is one of the reasons why you see most line integral written this way, vector using d vector x, instead of written using parameterization, because sometimes you don't know what the parameterization is, but you simply know the curve. Now, show you one last example on evaluating another trick. So here's my next example, and that will be our last example on evaluating line integral. You're going to have to gain more practice by doing the homework. So here's our last example, which is this. Let's say given vector f of xy equal to, how about x plus y, x minus y? Let alpha be the path that goes from 0, 0 to 2, 0, then to 2, 4, along two line segments. So let's take a look at what the graph look like. So here's y, here's x, here's the point 0, 0, here's the point 2, 0, and then here's the point 2, 4. So the problem said that go from 0, 0 to 2, 0, and then to 2, 4, follow along two line segments. So I would say here's my path. Yes, the arrow is important because the orientation or the direction of the curves is important. So, which is something that I kind of forgot to mention, but I guess I did say go from 0, 0 to 2, 4 along this path. So therefore, it did specify that the direction is this way. Okay. And some of you might be thinking, what happens if you go from like the opposite point to the beginning point? Then what would happen? Well, that would mean that your line integral will be reversed. So how about we calculate this? So what do we do? So now this one doesn't have any parameterization nor equation. Now we could definitely just go for figure out what it is. But let me write down a question first. Let's find the line integral of vector f dot d vector x. So how do we actually proceed with finding this? So the way to do it is actually pretty simple. The way I'm going to do it is I'm going to first kind of divide this alpha into alpha 1 and alpha 2. So basically separate this path into two of them. So therefore, imply that if I try to find this thing right here, what I can do is actually just, since alpha is basically a union between alpha 1 and alpha 2, and they don't have any overlap, that doesn't count to that they share the same endpoint, beginning point. That doesn't count. Therefore, I can just say, well, I can just simply find these two things individually and add the result. So essentially, if you think about it, basically the analog is that you basically calculate the amount of work being done, go from 0, 0 to 2, 0, and then add the amount of work being done to go from 2, 0 to 2, 4, which physically makes sense. So now the question is, then how do I find out how to calculate these two amount of work? Well, actually pretty simple in this case. Notice that alpha 1 is a complete horizontal line. And therefore imply that y is a constant. And because y is a constant, therefore we know that y is always 0. And more importantly, we know that dy is 0. Why? Because dy stands for the differential y. And differential y came from change in y. And in this case, because alpha 1 is horizontal, y is constant, and a constant doesn't change. So therefore, now allow me to calculate this. If I now try to calculate the line to go over alpha 1, basically what I'm doing is over alpha 1 of x plus y, x minus y dot dx dy. But dx dy go to 0, y go to 0, y go to 0. So therefore, this just now become a single variable integral, just dx. And if I'm looking at this correctly, it's actually go from 0 to 2, because that's what x go from 0 to 2 along alpha 1. And it become x dx plus x times 0, which is just 0. So it becomes just x dx. And this just come out to be 1/2 x squared from 0 to 2. So that just come out to be 2. So that's pretty easy. And now I can use the same exact logic to calculate alpha 2. Alpha 2 is vertical. And therefore, in this case, x is a constant. Because x is a constant, therefore x would have a fixed value, which in this case is 2. And dx will have to be 0. So now, if I look at the integral from alpha 2, I can see that this is just alpha 2 of x plus y, x minus y dot product dx dy. And in this case, dx go to 0, x go to 2. And since dx is equal to 0 and y go from 0 to 4 along alpha 2, because dx is 0, the 2 plus y would just times 0, which go away, plus 2 minus y times dy. So therefore become 2y minus 1/2 y squared from 0 to 4. So it'll be 8 minus 8, which becomes 0. So that's interesting. And so now we can actually finish up the problem and say, well, this just equal to 2 plus 0, which is just 2. So that will be my answer for this line integral. So notice that I can also take advantage of the path. If the path that we doing the line integral is actually horizontal vertical, it actually makes it a lot easier to just simply have the constant value and have one of the differential become 0, and then allow us to actually evaluate the line integral. Also, this example also illustrates that when you try to calculate line integral, if your path happen to be just horizontal vertical, it makes calculating line integral a lot easier to do because it has just one variable changing, which is nice. But of course, that's not always going to happen. Now, the last thing I want to show you is this. So this is the last thing I want to show you. And the last thing is actually one of the most important theorems I'm going to show you, which is called the fundamental theorem of calculus. And yes, you're probably thinking like, wait, didn't we learn fundamental theorem of calculus already? And yes, you have. The fundamental theorem of calculus that you learned before is basically for a single variable function. Now what we're going to deal with is a little different, okay? So of course you have already learned the fundamental theorem of calculus, but remember that's from BC calculus, which you're basically dealing with single variable function. And when you have a single variable function, the derivative is just a single variable function. What we're dealing with right now with fundamental theorem of calculus is, what if we have a multivariable function? Well, the problem with multivariable function is that the derivative of that is not a multivariable function of the same kind. Is actually called gradient. And what is a gradient? A gradient is a function that takes in a position and give out a direction, which is called the gradient vector. Notice that is exactly how a line integral, the vector f is. A vector f is a vector field, which is basically what a gradient is. So that's the connection that form what we call fundamental theorem of calculus for multivariable calculus. That is theorem 8.1.3, which states the following. Let f be a continuous and differentiable function, real value function, where f met from Rn to R. Okay. Let the gradient of f be, gradient of f is equal to vector f, capital vector F. Okay, important to realize the following. F, vector f being the gradient function, met from Rn to Rn. Okay. And let's say we have a curve. Let alpha be a curve in Rn, which starts at vector A and ends at vector B. Then, this is what the fundamental theorem of calculus states. If I evaluate the line to go over alpha of vector f dot d vector x, notice because capital vector F is the gradient of lowercase f, and based on what we learned in fundamental theorem of calculus, the integral and the differentiation cancel each other out. So here is the same exact concept. What happened is the integral and the gradient are actually cancel each other out and therefore result in this. Result in your line integral just being evaluating the function from the two endpoints and you subtract them. So notice that this fundamental theorem calculus looks very similar to the fundamental theorem calculus that you learned before. With the only exception is that we don't use gradient from before in your BC calculus. Fundamental theorem calculus, you would have f prime. When you integrate f prime, you just have f. And then you have to go from a to b, which is the interval from a to b. Here, a and b are both vector, and they define to be the beginning and end point of a curve. And the way the fundamental theorem calculus work is actually work with a line integral. Now, unfortunately, it's already past 30 minutes, so I don't want to make the video too long. So what I'm going to do is we'll go over an example together in class instead. So that way I don't have to make another video for just one example and post it. Okay, so that will be it for 8.1. We actually going to start 8.2 in our next video. But remind me to go over an example with you on Theorem 8.1.3 during class. All right, I'll talk to you guys on the next video. Okay, bye-bye.